All right, we're going to pick up section 14.2 and we're going to talk about integrated rate laws. And what we're going to do is we're going to take some calculus and we're going to apply it to the rate laws. So this is a slide where we left off. Remember that if you want to figure out the overall, what order the overall reaction is, you're going to add the exponents together. So here we have NH4 to the first times NO2 to the first. 1 plus 1 is 2. This is a second order reaction. So how are we going to deal with that? Well, what we can do is we can integrate these things. And when we integrate, we can kind of create a law or a mathematical equation for a reaction. So this is a first order process. I can't reiterate this enough. This is a rate law for a first order process. So the natural log of AT divided by AO is equal to negative KT. AO, or A0, is the initial concentration of A, and AT is the concentration of A at some time T during the course of the reaction. So it could be any time during the course of the reaction, that we measure the concentration, just not at 0. So A0 is the initial concentration, AT is the concentration at a given time. So this is our integrated law. Natural log of A over T is equal to A over O, which is equal to negative K times T. We can take this equation and manipulate it into this. The natural log of AT is equal to negative KT plus the natural log of A0, which in the one form or another represents Y is equal to mx plus B. So if I were to graph this integrated first order reaction, what would it look like? It would be a straight line, because a first order reaction is Y is equal to mx plus B. Right? Therefore, if you plot a first order reaction with the natural log of concentration versus time, it's going to give you a linear graph. So let's go ahead and let's do this with a first order reaction. Here we go. We only have one product. Therefore, that's a really easy way to consider. It's a first order reaction, and it's a 1-to-1 reaction. Perfect. So let's look at this. This data was collected at 198.9 degrees Celsius. So just like we did in 14.1, we measured, we had the pressure versus time, which is good for concentration since we're dealing with gases. Now, what we can do is when the natural log of P, which is going to be the concentration in this example, is plotted as a function of time, look at what we get. We get a nice straight line, which is going to show us that what order is this reaction? It is a first order reaction. Now, it is a first order reaction. If we have to solve for K, which is the rate order, all right, or the rate constant, K is the slope of this graph, and the slope of this graph is negative, and then you can solve just like you would change over y divided by change over x, and we solve for the slope is 5.1 times 10 to the negative fifth. So the slope of this graph is represented by K. Since it's a linear graph, it's a first order process. Now, what happens if we're going to throw in a second reaction and get a second order process? Well, similarly, we're going to integrate calculus, and what we're going to get is we're going to get 1 over AT is equal to KT plus 1 over A0. Again, AT is the concentration at a given time. A0 is the initial concentration. If we break this up, this is going to be our equation. If we draw this as a second order reaction in A, we will yield 1 over A versus T will yield a straight line. So let's take a look at this type of example. We have the decomposition of NO2 into NO plus oxygen. All right. Below we have our measured concentrations at a particular time. Plotting the natural log of NO2 versus T yields the graph at right. Is this a straight line? Absolutely not. Therefore, we know that this reaction is not a first order process. We use the first order reaction. The natural log of the concentration of AT, in this example NO2, versus T. When we did not get a linear line, we know that's not a first order reaction. So what we're going to have to do is we're going to have to graph this as a second order process. So when we graph this as a second order process, we're going to graph the natural log of 1 over the concentration versus T. And you can see now we get a nice straight line. Since we get a straight line using the 1 over the concentration of T, in this case, the concentration being NO2, since that's what we're studying, we see that we have a nice second order process in A occurring. So you are going to be studying first order processes and second order processes. We'll go back real quick. Remember, a second order process is going to be 1 over AT versus a plot of T will give you a straight line. In a first order process, excuse me, let me back up. I think I said first. In a second order process, 1 over AT is going to versus T will give you a straight line. In a first order process, the natural log of AT versus T will give you a straight line. So kind of comparing the two, first order versus second order processes. Now, you have studied this next term before, half-life. And half-life is defined as the time required for 1/2 of the reactant to react. You've studied this with Mrs. B before when you're talking about dating, radioactive dating in rocks and carbon-14 dating. Here we're going to study it kind of more in chemical reactions, and it applies to the same thing you learned with Mrs. B, but we're going to study it more intensely as it pertains to chemical reactions. So half-life is just when you've reached half your time. So what is the concentration after half your time is went through? Or how long does it take for half your concentration to go away? So because remember A is representing our concentration at T1/2. Here's the following equation. AT is equal to 0.5 times the initial concentration. So our half-life is really how long does it take to get us half the concentration. So if we do this in a first order process, we can plug in our 0.5 because we just figured out on the last slide that concentration in a given time is equal to 0.5 times our initial concentration. Well, we can plug all that in, and we can solve for in a first order process. The natural log of 0.5 is equal to negative k times 1/2 t. Mathematically rearrange everything. The natural log of 0.5 is negative 6 or 0.693. So in a first order process, to solve for the half-life, how long the half-life will be, very simply 0.693 divided by k will give you the half-life. Now this shows the steps in which you got there by plugging in our concentration of AT. In a second order process, we are plugging in, remember in our second order process, now it's 1 over AT, so now we're plugging in the 1 over 0.5 times a to the 0. We're plugging that all in. When we rearrange that to solve for the half-life of a second order process, 1 over k times the initial concentration is equal to the half-life. So we will talk about that in class a little bit more as we talk about how exactly do we calculate half-lives and how do they take this equation and rewrite them. So that is mathematically how we figure out a half-life. So that will conclude section 14.2, first and second order processes.